Good morning, everyone. I think it's time to start. I had a sleepless night because I couldn't figure out what we should do today. But I decided we'll just, I was contemplating that we could shift the brakes and all of this. But at the end of the day, I thought we get too distracted. Maybe I get too distracted. I just think of soccer. So we'll just do what we do. I think during the second break, it's in the game, so maybe we can put it on the screen if anyone's interested for 15 minutes. But then we have to get back to work. Okay. So we were talking yesterday about premix flames and flame structure. We talked about the flame structure according to thermal flame theory, and we said the thermal flame theory, everything is just based on temperature. The temperature gets larger and larger, and which means the exponential term gets larger. And then at some point, the exponential term gets so large in the reaction rate that things start to become interesting. But there's no real switching off of the reactions, no matter how small, how far you go in the unburnt mixture. The multi-step kinetics will be different there. We discussed this already yesterday, and we want to talk about the 4-step model, then also about a 3-step model, and then a 2-step model, which is then used to do the asymptotic analysis, and we'll see what comes out, and maybe also a little bit what's the difference to the thermal flame theory. So to talk about the 4-step mechanism, I mentioned the most important part is that you have different kinds of reactions: initiation reaction, chain branching reaction, chain breaking reaction, and propagating reaction. And one thing I said was you have to watch out for the radicals, always count the radicals in the reaction, and make sure you always count the O radical twice, okay? Because it can be converted very easily into 2 other radicals. Looked at this for a little bit, and I think this is from computation. We'll look at this later again. But so here we want to look at asymptotic description of the flame structure using the 4-step mechanism. To do this, we first start out to make the mechanism much simpler. Just consider the most important reactions, and then we come to a solution. And we'll see that this 4-step mechanism is for methane, but I tell you what the difference is for other hydrocarbon flames. And then finally, we'll use the results we get for an approximation formula. So the systematically reduced mechanism uses quasi-steady state approximations. So we assume that certain species, mostly radicals, they are formed, but then they're very, very quickly consumed, which means their concentration will always be very low, always be very small, and at the same time, it will not change very much. So this leads then to analytic approximations for these, for the mass fractions of these species. And so the species which are not in steady state, these are the species then that vary in time and space by transport and their interaction with chemistry. These are here the main species, so the reactants, the reaction products. Of course, they cannot be in steady state because that's the change from here to there is exactly what happens. Then we'll see hydrogen and CO are the main intermediate or stable intermediate species. They're also not in steady state. Actually, the radicals, the hydrogen radicals, also in steady state, but we don't set it in steady state because we want to see the influence of the dynamics of the hydrogen radical or of a radical on the flame structure. So hydrogen radical here is only used because to represent all other radicals also. You can look at the hydrogen as the radical pool for that matter. So right, so there are 2 important reactions that change the radical pool, and I mentioned this already yesterday. One is the chain branching reaction. This is the most important reaction that we have in combustion chemistry. O2 plus H goes to OH plus O. which produces radicals, and this is the main chain breaking reaction. O2 plus H plus M goes to HO2 plus M. And then the HO2, that reacts further to maybe H2O plus H goes to H2 plus O2. So that is where the chain breaking then comes in. Okay, and then we said if these are the two most important, the one the chain branching and the other one the chain breaking reaction, then we can actually compare the rates and see, you know, does the flame burn or not? Meaning if the chain branching is faster, the flame will burn. The chain breaking is faster, the flame will not burn. And this similar thing also is true for example, the explosion limits for hydrogen. And maybe you talked about this in Professor Pilling's class, where you also have a competition of these two reactions. So we said we can do this actually here mathematically. This ratio, if this ratio is equal to 1, then we say that is the crossover temperature. Above that temperature, you have chain branching. Below that temperature, you have chain breaking. This depends here on the pressure. It's shown here graphically for 1 bar. This is the chain breaking reaction. This is the chain branching reaction. And you see that above about 1000 Kelvin, you get chain branching. Below 1000 Kelvin, you get chain breaking. This does not depend on the fuel. It doesn't depend on anything else than the pressure here, really. I mean, this is for 1 bar. If this, for higher pressures, this line will be a little higher, and you see then chain breaking happens, or the crossover is at higher temperatures. At higher pressures, crossover is at higher temperatures. Flames will extinguish faster.
Can we just define that temperature as the ignition temperature?
Yes, you could call it the ignition temperature, but ignition temperature would mean, or you could think this means this is where the radicals are being formed. But here, really, the more important point is not that it ignites at that point, but you have a competition. So one side, this process is faster. On the other side, that process is faster, which is why we call it the crossover temperature. But that is, in the terms we used yesterday, that would be the ignition temperature, right? So here we call this the crossover temperature. We also call it the inner layer temperature, because that's really, we'll see later, that's where all the action is at roughly that temperature. Okay, so then we can look at you know, what happens to the species. If we look at we said this is a very important reaction here. This produces radicals, and we want to express now the action of this just by the species which are not in steady state. Steady state really means we have, for example, here in this reaction we form O, but we say this, so this here is a slow reaction. We always start here with the slow reactions, and then this reaction number 2, that's a reaction that compared to the first one happens instantaneously fast, is super fast. So you will, the result is you will never see the O radical, because once you form it, immediately it's converted to this OH and H. Okay, so that's how we can think about these steady state species. And then this reaction 3 is also infinitely fast. So infinitely quickly you will convert this OH, or these two OH radicals that you have now, to H2O plus H. Okay, so if we add these up, so you see here 2 OH, they go away with this, because this is, we multiply this twice with this, and then the O goes away with this. There's an H here, and there are 1, 2, 3 H's here, so 1 goes away and 2 H's are left. So if you just add all this up, you get the resulting reaction, which is O2 plus 3H2 goes to water plus 2H. So what this means is the first reaction is slow, but if it happens once, immediately this is the effect. Okay, so that's the global reaction, but that is a little bit a different global reaction from the global reaction where we said we have a one-step global chemistry, which just shows you, you know, the overall effect. This here is a systematically derived global reaction which gives the effect of this first reaction. And then also, what's the reaction rate at which this here proceeds? The reaction rate is the same as that of reaction 1 because this is the rate determining step, okay? So this happens only every 5 years once, and this happens in 10 to the minus 3 seconds, and this in 10 to the minus 5 seconds. So every 5 years you get this, and it happens with the rate of this first reaction, okay? So that's how we can think about this. And you see the chain branching character of this. Here you have no radicals, here you have 2 radicals. This is exactly what this reaction does. Then we have this reaction here. This is also a slow reaction. And so if we, this here forms HO2, and I mentioned this already, HO2 then is converted very quickly with H to H2 plus O2. And if we add these up, then we get H plus H goes to H2. The M here is not needed, really. But so here the M is not really needed. We just put it here because this reaction, Roman 4, that proceeds with a reaction rate of number 5, which is a pressure-dependent reaction. It goes with a third body, so we just add this here. So we see this. I mean, it's just for illustration purposes. Then methane is a little longer chain. Methane, I said this yesterday, if you have nothing else, no radicals, then it will be consumed with a different reaction. But in a typical premixed flame, you have radicals in the reaction zone. They want to diffuse into the preheat region and do some action there. And we'll see later on exactly how that happens. But this is the reaction that consumes methane. So methane plus H goes to methyl plus H2. And then the methyl radical, that's actually a quite stable radical. It's resonantly stabilized, and it's is not as reactive as other radicals. So in fact, you see the typical, what happens typically to radicals? So for example, if I have a radical, let's take a longer chain radical C, whatever, I have here butane, okay? And then let's say I take a radical away, take a hydrogen away here from this carbon, and I have a radical. What typically happens to this is what's called beta scission. So beta scission means you break this not on the first bond, but on the second bond from the radical position. So if I look at this, this is the first bond, this is the second bond. So either it would break here, and then I get here another radical, and here I get a double bond, or the other possibility is this and this. So this is the other second bond from here. So this could just go away, and what you get then is you get a double bond here. So you know, this, so very often you have a radical, and all it does, it just gets rid of other hydrogen. But here, there is no, for the methyl radical, there is no second bond, so beta scission cannot happen. So that's why it needs something more powerful to be consumed. And you see the main consumption reaction for this is methyl plus O goes to CH2O plus H. And what do you think about that reaction? This is chain breaking. Why? Because you have how many radicals on the left side? 3. And how many on the right side? 1. Okay, so this consumes 2 radicals. This, if you look at the whole reaction sequence here, then this should be really, I mean, it should get to your eyes. This should be a red warning flag, and you see, oh, this is the important part. So then you form formaldehyde. Formaldehyde here plus H goes to CHO plus H2, which means it's just what's called an H abstraction. So here one radical, everything good. Here exactly what I said happened earlier. This just gets rid of an H here, also because there's no beta seen here with a third body, CHO, CO plus H. And again, you know, one radical, and then that's basically it. So now we have converted this to CO, and because here we have an O radical, we just add these fast shuffle reactions here, again, to express it all in terms of the species we want to have in the mechanism, which is the stable species plus the H radical, the non-steady state species. Okay, so these are just added to get rid of basically here this O. This here gets rid of the O, but it gives you an OH, and so we add this here also to get rid of the OH in terms of the H. And so if you add these all up again, then we get methane plus 2H plus H2O goes to CO plus 4H2. This reaction, what's its purpose? It consumes the fuel. That's what it does. That's all it does. It consumes the fuel. We have one, now we have, this is the third reaction we have. The first reaction we had was the chain branching. The second reaction we had was the chain breaking. But that's not enough. You don't get there if you don't consume the fuel. So this here just consumes the fuel, okay? And you see what it does. It consumes the fuel and breaks it down to the stable intermediates. So the first step that happens in a flame, you take the fuel, you break it down to stable intermediates, which for hydrocarbon flames then are CO and H2, okay? That's it. And you see, this is not for free. You cannot very easily get rid of the methane and convert it to intermediates. How do you see this here? Is a very hard thing to do, obviously. How do you see this in this reaction? Well, CO and H2, that mixture is called syngas. But now, how do you see in this reaction that methane is very hard to consume? Yes, the radicals go away. I mean, in order to convert one CH4 to CO, you need two radicals. You need to pay a high price, okay? The CH4 comes and says, okay, I'll do this, but it costs you two radicals. So you have to put money on the table, or radicals on the table. So methane flame speeds are not very high. Okay, now you know why. It's very simple. It consumes radicals. So three things in this reaction. Number one, it converts, this consumes the fuel. Second, it converts it to stable intermediates. Third, you have to pay radicals to do that, okay? So this is the step. Now think of a different fuel. Think you have heptane or here this butane or whatever. It has a very similar reaction here, and on the right-hand side you will have CO and H2, okay? And the only difference between the different hydrocarbon fuel, maybe not the only difference, but let's say it in simple terms, the difference is how many radicals you need to break the fuel, to convert the fuel to stable intermediates. If you have now, you know, well, different fuels that don't need radicals, then you will see also they might have a higher burning velocity. Okay, so now we have CO, and we need to get rid of the CO. What do we do with the CO? The fastest, most important CO oxidation step is CO plus OH goes to CO2 plus H, and that's it, okay? And we need an OH, which is why we add this fast shuffle reaction, and then you add these up, and you get this reaction, which is called the water-gas shift reaction. You see, it takes CO and converts it to CO2, and the hydrogen back to H2O. So this reaction is often used. That's why it's called water-gas shift reaction. If, for example, if you want hydrogen, then you would first consume fuel here with maybe even with water. That's one technology, and just have this first step here happen. This is called gasification. So you and this here is then the syngas, and the syngas then you have one CO 4 H2. Let's say you want more hydrogen, then you would adjust the temperature so that this here is shifted to the right direction. This does not depend on pressure, of course, but you can choose the temperature so that the equilibrium will be on this side. If you have a different day, you want carbon monoxide for whatever reason, you would adjust the temperature here to shift it all to the left side. Okay? So one technology that is used for carbon capture is, for example, gasification here to these species. Then you shift this all to H2 and CO2, and then you burn this, which gives you then H2O, and then you have here, you have the CO2, okay? So there's a technology is called integrated gasification combined cycle, which tries to do this, to have as a carbon capture technology. Okay, so these are the 4 steps then, and each one has a purpose. Fuel conversion to stable intermediates, CO oxidation, chain breaking, chain branching. That's it, okay? And this I showed you already. The reaction rates of these are we call this the principal rates. The principal rates is what you get when you say all reactions are infinitely fast except for the first one is slow. Then always the whole process goes with the first reaction. So for the reaction 1 here, fuel consumption, it goes with this reaction. The CO oxidation goes with this reaction rate. The chain breaking goes with the reaction rate of this reaction, and chain branching here with the reaction rate of this reaction. So that's the 4-step mechanism. Now, because we need to, if we want to use this maybe, even in a simulation, or if we want to use it for analysis, you see that the reaction rate here of this reaction goes with the concentration of CO. Yes, that's a non-steady state species that we still have in the system, and but also with the concentration of OH. We don't have we don't solve for OH here because it's a steady state species. So for OH, we need to have a relation, and also for the O radical. And so this is what we get from. We assume that this reaction is in equilibrium, in partial equilibrium, which means then that I can. So this here is Kc. Then so if this is in partial equilibrium, I can get the O concentration here from just from evaluating the equilibrium constant of that reaction. Okay, so remember we said if we have a reaction, I'm not sure if that's clear now for everyone. If we have this, take this first reaction here, O plus H2 goes to OH plus H. Okay, then we say Kc, the equilibrium constant is COH times CH divided by CO times CH2. Right, so this is what we did yesterday, which means now I can solve this for CO, and I have so this is only a function of temperature. So if I know the temperature, I know the concentration of H, I know H2, and that gives me the O concentration as function of OH. And if I do the same thing here with this reaction 3, then I get OH concentration as function of water, hydrogen, temperature, and H2. And these are all species I know. Okay, so that just closes the system. These are then the reaction rates. And you see here is even the reverse reaction is included for this reaction 2 and 4. And so now there are 4 reactions, and the reaction rates, they are all expressed in terms of the concentrations of these species that appear in these reactions. So that means that this can now be solved. This here, I showed you yesterday how to compute these easily, how to compute these equilibrium constants, and they're also given here. So this has all the numbers you would need if you want to code up this four-step mechanism, you could solve equations here for these species that appear here: methane, hydrogen, H2O, CO, and maybe that was and oxygen, and that's it. Okay, so so that's interesting. Now we have a description of the chemistry in this. That's relatively simple because it has only 4 steps. Okay. Now, one thing that's very instructive is to derive from this a 3-step mechanism. Why is this instructive? What I want to do now is I want to set the hydrogen radical in steady state. And if I do that, then I get an analytic expression for the concentration of hydrogen. And if I have an analytic expression for that concentration, I can see analytically, I mean from an equation, I can see what happens to the radicals. Hydrogen is just representative for all radicals. What happens to the radicals? Where do they come from? Where do they go? And all of this. So that's what we want to do. So take this mechanism, and now we just add step 4 to step 1, this here to this, and you see then the hydrogen goes away. The hydrogen radical goes away. We get CH4 plus O2 goes to CO plus H2 plus H2O. Okay? So that's now the fuel consumption that converts the fuel to hydrogen and CO. And then we add reaction number 4 to reaction number 3. And then again, the hydrogen radical goes away, and we get O2 plus 2H goes to 2H2O. Okay? So now you see these, you see even more clearly what we knew before already. Here, this forms CO and H2. This oxidizes the CO, and this reaction here actually oxidizes the H2. And so here you see the same thing without the radicals. What's interesting now is I can take this reaction here, these reactions, and say, so from the 4-step mechanism, I can say, what is the rate of change of the hydrogen radical? dCH dt is equal to minus twice omega 1, and then where do I have hydrogen radicals? Minus twice omega 3, minus 2 omega 3, and then plus 2 omega 4, plus 2 omega 4. Right, that's the rate of change of hydrogen. But now I want to set this steady state. Steady state meaning this has to be 0. So this now is equal to 0, which means if I have an analytic equation that includes the hydrogen radical, which I can solve for the concentration of hydrogen. Okay, so that's done here. This is the expression that I just wrote down here, and these are the rates. Here's omega 1 includes hydrogen, omega 3 includes hydrogen, and omega 4 also includes hydrogen here and there. And so you see this hydrogen goes away, and what's left over is this hydrogen here. And then I can solve this for hydrogen concentration, and this is what I get. With this here, H equilibrium, it's just an abbreviation, okay? So at the end of the day, this is the factor that is in front of this, and by coincidence or not, this factor is equal to the hydrogen, the equilibrium concentration of hydrogen if this reaction 4 here was in equilibrium. But that's just, just look at this as an abbreviation for this term. Okay, so now this is interesting because we can try to understand what happens to hydrogen, okay? And there is actually an interesting lesson to be learned. So at temperatures above 1400 Kelvin, high temperatures, the second term here in the brackets becomes very small. That's what we saw earlier, okay? So the first one here, because this is both divided by K1, the chain branching reaction, So the first term here is basically the chain branching by reaction 1. And this here, this ratio, that's what we said earlier, for high temperatures, this becomes much, much smaller than 1, okay? So at high temperatures, this here is actually small, and the ratio, K11 divided by K1, is very large, okay? What does this mean? If this ratio here is very large, you see this is 1 minus this term and the square root. So you only get a real solution if this term here is smaller than 1, okay? Which means if K11 divided by K1 is very large, then this here must be very small. CH4 must be very small, okay? Otherwise, you cannot get a real solution to that equation, okay? It means basically hydrogen cannot exist. So, for hydrogen to exist, you cannot have methane. Isn't that interesting? That's what the equation tells you. Methane and hydrogen cannot exist at the same time. Which means, but you need hydrogen to convert. So here's you have the flame, okay, the reaction zone. Here's the preheat zone, so the methane comes in. And the hydrogen tries to diffuse into the preheat zone. But as soon as it meets a methane, you know, it's gone. It's consumed, because you saw earlier, methane consumes hydrogen radicals. So it's gone. Methane and hydrogen, they cannot coexist at the same time, okay? That's what this tells you. That's interesting, okay? So, right, so hydrogen radical cannot exist in the preheat zone. And that's why the preheat zone is chemically inert. This is shown here. So let's see if this is true. Okay. This here is so the inner layer temperature here. That's above this. That's where the hydrogen radicals are formed. Okay. So this hydrogen radical concentration, and when you get to this point here, then the hydrogen radical goes to 0. Why does it go to 0? Because the methane radical comes from the preheat zone, and they go to 0 here at the same time. I thought I had a plot that shows also the methane molecule, but I missed to put this in here. Maybe I should do this for next time. But you see that hydrogen exactly here at this 1050 goes to 0. Exactly what we assume, what we see from the theory. Right. So, okay. So that's what the three-step mechanism tells us. Is just this fact that the hydrogen and methane, they cannot coexist. As soon as they come together, they react. Okay. So now for the asymptotic analysis, we can further reduce this. There has to be a coupling now to reduce this further, because you cannot reduce another species. So here the further reduction is done by coupling hydrogen and CO. And so there is a new species here, which is hydrogen plus alpha CO. And you know, that just appears here as one species. So hydrogen and CO appear as one thing, and they're treated as one species. That's how you get from 3 to 2, but it makes the analysis simpler. Now, one thing I missed to say is that is an interesting fact. So you see here now that we have a preheat region. We have this inner layer. That's what we just said. The inner layer is the point or the region where the temperature is equal to the crossover temperature. And that is exactly where you convert the methane to CO and H2. And then there's an oxidation layer that converts CO and H2 to products, to CO2 and H2O. Now, one thing that's interesting also is when we talk about a four-step mechanism, let me go back to this. Four-step mechanism, what does this really mean? You have four different reactions. There's no reason why two reactions should happen at the same speed, okay? So each one of these reactions you can think of happening at a different speed. So each reaction then has an own timescale, which means you have really four different timescales here. This reaction is relatively fast. This reaction is relatively slow. This reaction, no, it depends on where you are. We saw this already. Low temperature it becomes fast, high temperature slow, and so on. Each one of these has its own timescale, okay? Which is really why they're there. If you have two reactions which have exactly the same timescale, then they don't need to appear both. Only one of them needs to appear. But in one-step chemistry, you have only one timescale. That's it. You have only one reaction, one timescale. This shows you that you need at least these four different timescales if you want to describe these four different effects that are relevant. It also means, and that is a consequence, if you have a premixed flame. So let's say you have a flame that is, let's say I have a flame that sits here and it burns in this direction. So this is unburned and this is burned, okay? Then I have a convection, I have a flow that goes this way. So if this flow comes in here, and then it starts, so this heats up now, and it comes to the inner layer, it has inner layer temperature. Then this reaction happens, and it has a certain time scale, and it will be done a certain time later. If I take this, this time scale, let me see, this would be T. If I take this time scale, T, reaction, any one of these reactions, and divide it by the velocity, that gives me a length, right? That gives me the way that this gas has traveled during the reaction time, okay? So this divided by SL really is the velocity. That gives me a thickness, L. Gives me a thickness. So the velocity is the same for all reactions. But because each single reaction has a different reaction time, the region over which it happens is different, right? If I have a very fast reaction, like, for example, I said this first one here, if I have a very fast reaction, then this layer will be very thin. If I have a very slow reaction, meaning the timescale is large, this layer also will be very large, okay? This is why in a flame you have different layers corresponding to different timescales that correspond to different reactions, okay? So this is then what's shown here. This is what's shown here. You have the preheat zone. That has nothing to do with the reactions. It's just heating up the few layer mixture. But then there is an inner layer, which is where where this reaction happens. And then you have an oxidation layer, which is much slower, where this reaction happens, okay? So if oxidation was much faster than this first reaction, then you wouldn't see this layer. It would be a part of this, right? It wouldn't form an extra layer. And that's what these other reactions do. That's why you don't see them anymore. So we said, missing my chalk. So we said we have methane, CH4, plus H goes to methyl plus H2, okay? We said that's the first reaction that happens, okay? That has a certain time scale, which corresponds to a certain length. But then there's a second reaction that happens, is CH3 plus O goes to CH2O plus H, okay? That happens after the first one, downstream, with a different time scale. but because this time scale is much, much faster than this, you don't see an extra layer. This happens at the same time, okay? So only the slow reactions give you these layers. But here then we have two chemical layers. If you would consider the three-step mechanism, you would have one more layer, and the four-step mechanism would have one more layer, okay? Okay, anyways, so this has three layers, the preheat region, the reaction zone, which is very thin, and then an oxidation layer, which is much larger. So here we say this is of order delta, this is of order epsilon, and epsilon is much larger than delta. And both of these, both delta and epsilon, are much smaller than 1, or much smaller in the preheat region. Okay, so this gives you now the details of the analysis, which we are not going to go through. There's a lot of, you see a lot of stuff here, and we'll just flip forward to the result. This is the result, and in a sense, you could say it looks a little similar to what we had from the thermal flame theory. But there are some differences here. One is that you see the inner layer temperature appearing here. Now, there's no surprise. We said that's one of the most important concepts. The inner layer temperature is determined from this reaction, from this expression, which is really very similar to what we defined. Here, the small difference is that earlier when we defined the inner layer temperature, we said the only chain branching reaction is number 1, the only chain breaking reaction is number 5. Here also the effect of reaction 11, which consumes the fuel and then very quickly leads to the consumption of these two radicals here. That's also considered. So this ratio is equal to something related to pressure, and so typically what you could do here is you fix the pressure. You say, I want to know this for 1 atmosphere, and then I have to solve this, but this is nonlinear, so it's complicated. You could also specify the inner layer temperature, and then from that get the pressure for which this is. So that's done here. This is basically here, this line is the inner layer temperature as function of pressure, inner layer temperature, and then for 1 bar we can just say, okay, this is the inner layer temperature, and then this line here is SL as a function of inner layer temperature, okay? So this is the inner layer temperature for 1 bar, 1400, and then I can say, okay, that's then for 1400, this is the SL here. So I get something like 55 centimeter per second. 54 centimeter per second. We said last time the laminar flame speed for this obviously for stoichiometric conditions. Stoichiometric conditions is a little less than 40. So it's not totally accurate, but it's the right order of magnitude, and it gives you the right trends. So you see here again, there is basically a chemical time scale, and there must be somewhere here lambda over rho Cp, okay? So this is the same thing we had last time. This must be somehow the SL must be somehow square root of d divided by Tc, bidimensional arguments. And d is equal to lambda over rho Cp, and then all the rest must be the chemical time scale, okay? So that's, and one thing that we see that is very different from what we had earlier is that the flame speed can go to 0. When does the flame speed go to 0? This is not so difficult. When does it go to 0? Right, so when the temperature, the adiabatic flame temperature That depends on the mixture. If you go lean, it goes down, okay, because now you have excess air, or you go very rich, it also goes down. So, but this here does not depend on the mixture. So when TB is equal to T naught, then the flame will extinguish. Yeah, then SL is equal to 0. Okay. So, okay, so that just shows again these are the reactions that play a role. This is the same thing here. Nothing else. This is what I just mentioned. When TB reaches T naught, then this will go to 0. Let's see. Then there is this now. I mean, you can take this relation and compare it with the result from the thermal flame theory, but this is just a result. I mean, you can go through this. What we saw earlier was that the reaction zone thickness was on the order of the inverse Zeldovich number. Remember, we had the Zeldovich number squared appeared in the relation. And here for this two-step model, it turns out that the oxidation layer thickness is on the order of the inverse Zeldovich number. So the oxidation layer for multi-step chemistry plays the same role as the reaction zone for the one-step theory. And that makes sense because there we just looked at the thermal effect, just at the heat release, and the heat release here really comes in the oxidation layer, okay? Okay, so then we can quickly look at an analytic expression for the burning velocity. This is something that's quite useful, you know, for doing reduced order modeling or for trying to understand, you know, how things change. You can now take this expression here for the burning velocity and try to write it in a more general form. So here, for example, there's TB minus T naught to the 4th power, or divided by TB minus TU to the 4th power. So we keep this relation here and have not the 4th power, but have the power as a parameter. And then here is the fuel mass fraction that stays here. And then there's a big temperature-dependent part, and we just express this here by an exponential function with 2 parameters. So we write, then also we have here the T naught as a function of pressure. So if you write it like this, the functional form is very similar to this, but you have a lot of parameters here, M, N, B, and so on. These are all free parameters. Then this is done in this paper here. These guys, they did a lot of simulations for different fuels, simulations determining the burning velocity for different temperature, pressure, equivalence ratio, and so on, all for lean flames, actually, here for all these different fuels, and between you know, these pressures, these temperatures, equivalence ratio, and then fit the data they got from this, and then these are the coefficients. And now, if you have these coefficients, you can put them in your code. You have these expressions here, and you can very quickly compute the burning velocity at any condition you want, okay? So this, if you ever want to use this is probably not so bad. I mean, this shows here comparison with experiments. This is the burning velocity for methane, functional equivalence ratio for different pressures. And you see, it's not so bad. Not perfect, but not so bad. This is here, for example, propane at different temperatures as function of pressure. And also is not perfect, but it's not so bad. The mechanism that was used for that is probably a little old. And if you ever want to use something like this, maybe it's a good idea to just refit the whole thing. But the basis function for the fit is very good. That also should give you an idea for maybe for your research, because very often, if you want to fit something, if you want to express something, then it's sometimes, if you, in combustion always we have these very strong nonlinearities. Sometimes it's very hard to fit things. But if you have a good basis function, then it's very easy to fit, okay? And while the analytic solution we have from the asymptotic theory while it's not perfectly accurate, you see what the dependencies are. You know this will depend on TB minus T naught to the fourth power or to some power. And so that will give you an idea for a good basis function. Whenever you do fits, we do this a lot. Whenever we want to tabulate something, we first think about what is a good basis function to do the fit. And for example, if you have something that is a very simple example, if I have something that depends, so a reaction rate typically depends on the square of the pressure. If I want to fit a reaction rate as function of pressure, if I want to do, let's say, a Taylor series expansion, I need to have two terms, okay, to get a. But if I do the Taylor series expansion for the reaction rate, but for the square root of the reaction rate, then I need only one term, okay, because then it's linear. So that's very simple. Now, if you have a very complex exponential function and you want to fit that, then you need many, many terms in the Taylor series. But if you have if you fit instead of, if you choose the right basis function, you know, which just takes this, you know, weird exponential into account, then fitting is very easy. So that's exactly what this does. So even if you don't use the exact numbers that are here, it's a good idea if you ever want to do something like this to use a basis function of this kind here. This also shows you, I mentioned this before, the burning velocity depends very strongly. Remember I said this when we looked at the adiabatic flame temperature for different fuels, and we said unsaturated fuels have a higher flame temperature. I said burning velocity depends very strongly on flame temperature. That's what you see here, TB minus T naught to the nth power. So it's a very strong dependence. That also explains why when you go lean, why you get a very strong dependence on equivalence ratio, because if you go lean, then TB will get smaller, and if it approaches T naught, then you see all of a sudden you get a very strong, as long as TB is much larger than T naught, this doesn't change very much, but if TB comes close to T naught, then this term here, it will change very strongly with equivalence ratio, which is why when you go very lean, you get a very strong dependence on this. Okay, this just shows an example here. Let me just check the time. So we have a few more minutes. Okay, so this just shows an example which you can go through. Another aspect that is very important and is flammability limits. There are flammability limits below a certain equivalence ratio. For example, it's shown here. Below a certain equivalence ratio, you have a fuel air mixture and you want to ignite it, you want to spark it, it won't burn. So that's very important for safety. For example, in your gasoline tank, gasoline is a little more volatile. So typically the mixture that you have in a gasoline tank, the mixture that you have above the liquid is so rich that it won't burn. It's outside the flammability limits. A good trick for gasoline. For diesel, it's the opposite. Diesel doesn't evaporate very easily. So typically the mixture above the diesel liquid surface is so lean that it wouldn't burn. So if you want to mix diesel and gasoline in your gas tank, maybe it's not a good idea. You get a combustible mixture, okay? So this here shows, this here is actually not the fuel-air ratio, but it's the air-fuel ratio. Lambda, we talked about this on Monday, so is 1 divided by equivalence ratio. So this here is rich, and this here is lean. This is just how we had this plot here. And you see this here are the flammability limits for methane as function of equivalence ratio and temperature. And these are the limits for hydrogen. And you see that this here is the rich part. Hydrogen ignites under more rich conditions, but especially here under lean conditions, you see if you are at an equivalence ratio lower than what is this, 3/2 is 2/3, 0.6 or something, then methane wouldn't burn anymore, but this goes up to 0.3, equivalence ratio of 0.3. So hydrogen is very dangerous. If you have a small hydrogen leak, it can lead to an explosive mixture very quickly. The question is, how can we explain the flammability limits? And we said now, well, if TB is equal to T0, then the flame can't burn anymore, okay? TB is a function of equivalence ratio, and so we can express TB as a function of equivalence ratio, and we can see where is TB equal to T0 to determine as function of equivalence ratio to determine the flammability limits, okay? So we say this is kinetically controlled. Flammability limit is when the chain branching becomes slower than chain breaking, okay? And so we can use here this approximation formula, for example, to do this. We have all these values. These are all these coefficients. We have these in this table I showed you earlier. And so what we do here then, so this is the coupling function for fuel and temperature. So this is for the lean limit, let's say. This would be the mass fraction at the lean limit. And this is when TB is equal to T0, so we put T0 here. And then we can write this also for stoichiometric condition, divide one by the other, then we get rid of this Q ref here, and we get this expression. So you see here, this mass fraction at the lean limit is then given here as function of the mass fraction at stoichiometric conditions, which we can easily determine. So if we evaluate this prefactor here, then this is what we get. So this tells you this is the mass fraction. This is the mass fraction at which the flame would go out. Corresponds here to an equivalence ratio of 0.46. And if we compare that now with data, so this here is the lean flammability limit for methane as function of temperature. This is from data. This here shows you simulations here of the burning velocity. So most of the data here shows a burning velocity of about 5 centimeters per second, not 0. This is the line we just determined. So you see this underestimates the flammability limit. So this just means, but actually the trend is pretty good. So this very, very simple notion that flammability limit is kinetically controlled, and it happens when TB is equal to T0. Doesn't give you exactly the right answer, but gives you the right trends. And the reason for the difference here is that there are other effects that are important. For example, when a flame burns very slowly, then the residence time is very long, and radiation becomes important. So you have radiative heat losses. So flames below a burning velocity of, let's say, 2.5 here or 5, they can't burn anymore, for example, because of radiative heat losses. Okay, so that's just to say, if you try to do the same thing with a thermal flame theory, there is no limit. Okay, there is no limit. For whatever you do, the burning velocity never gets 0. Okay, you can make TB as small as you want, then this just gets smaller, but it doesn't get, it's not 0. Okay, so that actually concludes this topic, and maybe we'll take a break now. Exactly, we're exactly on time, so we'll continue at 10.